If you're in high school, you may be learning about these formulas, but you probably don't even know where these come from or why they work. And sometimes it can be super frustrating, because when you don't know why something works, blindly trying to apply it makes it even harder to remember, and makes it feel confusing. So today what I'm going to show you in this video is some visual and numerical intuition to help grasp these formulas and some proofs. If at any point in this video you feel like you have an idea of what to do next, I encourage you to pause and try to work it out. Before we get to triangles, let's start with circles, namely the unit circle. This is a circle that has a radius of 1. One of the properties of a circle is that all the points are the same distance away from the center. Another thing we can do is draw a line segment from the origin and some point on the circle. Because the circle has a radius of 1, no matter which point we choose on the circle, the length of the line segment will always be 1. We can also measure the angle that this line segment makes with the x-axis. We'll call this angle theta. Sometimes you'll notice that two angles look completely different numerically, but when graphed show the same line. These angles are called coterminal angles. This isn't too relevant to the trig identities I'm going to show you, but it is nice to keep in the back of your mind. Also, quick note, just remember that pi radians are equal to 180 degrees. On the line segment, if we label the point at the origin A and the point on the circle B, we can drop down from point B until we reach the x-axis, creating a new point C and triangle ABC. Now that we have our triangle, we can begin labeling sides relative to theta. Just by looking at it, this side is the longest, so it's the hypotenuse. We can also label the adjacent as the side next to it, and the opposite as the side that does not touch the angle. From here, we can apply SOHCAHTOA and figure out what the trigonometric functions mean relative to this triangle. If we look at sine, it's defined as opposite over hypotenuse. Since we know our hypotenuse is 1, and dividing any number by 1 keeps it the same, we now know that the opposite side is equal to the sine of theta. We can apply a similar logic for cosine. Cosine is adjacent over hypotenuse, so the adjacent side is cosine of theta. In terms of x and y coordinates, we can say that cosine, being the horizontal side, is x, and sine, being the vertical side, is y. Because this is a right triangle, something we can also do is use Pythagorean's theorem. If we apply the theorem to the right sides, we get sine squared plus cosine squared equals 1. And finally, with all those basics out of the way, let's move on to the formulas. Why can you do this, but not this? While this normally comes down to whether a function is labeled even or odd, I'd like to try to explain what's really going on. Looking at it graphically, making the angle negative flips it on the x-axis. Doing this causes the x to stay the same, but makes the y negative, which is why cosine stays the same, but sine becomes negative. Now that we've found an angle where the x is the same, can we do the same, but for y? The answer is yes. Over on the other side of the circle, there's a spot where the y will be the same. It kind of looks like the same angle, but flipped. But how do we represent this? What we can do is start from pi and then move the angle backwards. This is equivalent to subtracting the angle. From here, we get sine of pi minus theta equals sine of theta. By looking at the x value of this, we can see it looks similar, except it's negative. While this formula isn't that hard to remember, it still feels very arbitrary. For this proof, we're going to temporarily abandon the unit circle in favor of triangles. Let's label the sides and angles of this triangle. The angles will be alpha, beta, and gamma. Opposite to alpha is A, to beta is B, and C is gamma. First, line up the triangle so that one edge is horizontal. Then, from the top of the triangle, draw a line straight down. We'll label the length of this line h for height of the triangle. Now, since we've made a right triangle here, let's take the sine of angle alpha, which will be opposite over hypotenuse. In other words, h over b. We can do the same thing with angle beta, and the sine comes out to be h over a. Now that we have two equations, we can solve both in terms of h. Multiply by a here and b there, and we get b sine alpha equals a sine beta. Divide both sides by ab, and we get our sine law formula. Since the side we chose was arbitrary, this works for the other angles as well. And just as a bit of initial intuition, this kind of looks like the Pythagorean theorem, but with this extra bit attached. Since we're subtracting this part, you can think of it like the angle is shrinking the line, and this part tells you how much to shrink by. But how do we know that it's exactly this? First, let's start again with the same triangle we had before. Draw a line straight down again, and label the point where it touches the triangle on the bottom as D. Let's label the original base length we had as B, and this section as B1. We can also say that this section is B minus B1 in order to keep it consistent. Let's also label this side length as H again. Now, let's take the cosine of alpha. Since cosine is adjacent over hypotenuse, we can say it's equal to B1 over C. Rearranging this in terms of B1, we get B1 equals C cosine alpha. We can also do something similar for sine, where it's equal to H over C, or H equals C cosine alpha. Using Pythagorean theorem, we can find the length of this side as well. The bottom leg is B minus B1, and the left leg is H. So we have A squared equals B minus B1 plus H squared. Substituting in what we got for B1 and H, this is what we end up with. Expanding these terms out, we're starting to get very close to the formula. From here, we can factor c squared out from these two terms, and we're left with c squared times cosine squared of alpha plus sine squared of alpha. From the intro, we know that cosine squared plus sine squared equals 1, so we can simplify that to 1. With that, we have completed the cosine law. If you want, you can go even further and take the square root of both sides to leave it purely in terms of a. While this is a very powerful formula that helps you get more precise angle measurements, it's also very unintuitive at first glance. Like, what is cosine doing here? Why are they being multiplied? How does this actually work? Firstly, let's visualize what stacking two angles looks like. Let's draw angle alpha and put beta on top of it, labeling the origin A, the point on the circle where it intersects, as B, and dropping down from that point to reach point C on the x-axis. We now have a right triangle ABC. Since we're back on the unit circle, this length is now 1, and now sine of alpha plus beta, which is what we're looking for, is now this line. Before we continue, let's imagine that we're trying to take just the sine of beta. If we were to do that, we'd have angle beta on the unit circle, and make a right triangle this way. Let's label these side lengths as sine and cosine of beta. Now, if we rotate this triangle so the side length one side matches up with our previous diagram, we can label a few more points. Let's label this right angle point D, and drop down to create another x-axis intersection point E. Directly to the left of D, we can label this point F and make a right triangle BFD. Once we label this intersection point here as G, we are ready to begin. We're trying to find the length BC, which from the diagram can also be broken down as BF plus FC. In rectangle CEDF, we can see that FC and DE are the same because of the properties of a rectangle. Take a moment to verify if this makes sense. Since FC and DE are the same, we can also say that BC equals BF plus DE. DE happens to be the opposite side of angle alpha. Since we already have the opposite and hypotenuse to find for angle alpha, we can say that the sine of alpha is equal to DE over cosine of beta. Multiplying both sides to get DE, we have DE equals sine of alpha times cosine of beta. Remembering that a triangle's angles need to add up to 180 degrees, we can do some angle chasing to label some angles. Once we get all the way up here, BF happens to be the adjacent to angle alpha here, which is what we're trying to find. We also know BD, which is the hypotenuse of this triangle. With these, we can determine that cosine of alpha is equal to BF over sine of beta. Multiplying both sides by sine of beta, we get cosine of alpha times sine of beta is equal to BF. Now that we have our two parts, let's add them together to get the formula. With this formula, you can also derive certain things like the double and half angle formula. Let's reuse the same diagram, but clear up some of the labels we won't need. This time, we are trying to find length AC, as that is the cosine of alpha plus beta. The first thing to notice is that AC can also be broken down into AE minus CE. For a similar reason as before, using the rectangle, we can substitute DF in for CE. We can find DF pretty easily. The sine of alpha is DF over the sine of beta. In terms of DF, this is sine of alpha times sine of beta. AE is the adjacent of angle alpha, so cosine of alpha is equal to AE over cosine of beta, or AE equals cosine of alpha times cosine of beta. Here's our formula. While these formulas are mainly taught as things simply given to you, it helps a lot if you can visualize where and how exactly these formulas come about. Many formulas make a lot of sense if you can just get the right diagram to understand it. However, once again, in 3v1 Brown's video about fake visual proofs, it also helps if along the way you make sure to check and see that everything makes sense up to that point. However, trigonometry is a subject that highly relies on visualization to understand. In fact, I don't have time to show them in this video, but you should try to create a visual diagram for yourself to show how to prove these two theorems as well. Sometimes, you may have to try and make some decisions that feel somewhat arbitrary, but experimenting with them will help you lead closer to the results. I want to give a shout out to 3v1 Brown for starting the Summer of Math Exposition Challenge, as it helped motivate me to make this video. Thank you for watching.